Everybody, I'm Luigi Nardi. I'm the founder and CEO of DBtune. Today we'll be talking about auto-tuning Postgres, a deep dive into server parameter tuning with Agentic AI. So let's get started, but let's just also introduce myself very briefly. I have a mixed background in industry and academia. Among other things, I have a computer science, PhD in computer science degree, and I was a research staff at Stanford University and an associate professor at Lund University in artificial intelligence. Since 2020, I founded DBtune. All right, so this presentation is heavily inspired by the work that we do at DBtune. DBtune is an AI-powered database tuning service. It's a spin-off from Stanford University. And I really would like to take some real-world examples from that experience and bring it in this presentation. The rest of the presentation will be fairly generic and be used in other contexts, but the examples towards the end will be related to some real-world experience that we have building auto-tuning systems in the real world. And this is really the idea of making Postgres, specifically the database that we will focus on today, Postgres, specific to a workload and a use case and a machine. So taking something that comes shipped in a fairly generic form and doing tuning to make it specific to your use case. But let's start by defining from a high-level perspective what database performance tuning is. So this is really the idea of keeping the database fit and responsive. So databases change, grow, and slow down over time, and not all workloads and machines are the same. So tuning is literally this process that adapts a database to its current use case, load, and machine. This is a bit of a dark art. It's usually the job of a database administrator and a developer, or these days, developers do the work of maintaining databases as well, which is a bit of a shift in the industry as well. Platform engineers as well are part of this. And it's considered a little bit of a dark art because you have to do a lot of manual try and error to get this right. And this is a very long and tedious process to get it right. And when we talk about tuning, very often we talk about many different things. We talk about rewriting the SQL statements, for example. It's also referred to as query tuning. Talk about server parameter tuning. We talk about index tuning and operating system parameter tuning and so on. There are other things that you can tune in a system in general. And today in this presentation, we'll focus on the server parameter tuning part. That being said, all the other parts are equally important. So the focus of the DBtune is on server parameter tuning, but we should consider any single tuning part for in general to really make the service of database really performing well. Just want to spend a minute on why does it matter, and there is of course a technical perspective. So people like me care a lot about throughput and latency and how to improve scalability, stability, and SLAs. But there is also a business perspective, of course, and this is actually highly related to tuning and the health of the system, the throughput, the latency. So if we get better throughput and better latency, what we get is higher end user satisfaction. We can achieve a better or more optimized infrastructure spend, and most importantly, reduce downtime. So very often downtimes are led by a bad performance of the system. And so by tuning the system, we can achieve this better reduction in downtime periods. And we can also increase the productivity of the overall team and save energy in the process. When software is well optimized, it's also energy efficient. All right. So database system parameter tuning, specifically, we'll talk about Postgres here mainly. And this is really the idea of adjusting the parameters, or sometimes called knobs, to best fit the workload. The problem really looks like this picture on the right of the screen. So you have all these different parameters that govern the way the disk, the memory, and the CPU and the planner, all these things kind of interact together. And the idea is to find the best values for these parameters in a way that you achieve high performance. So these are some of the examples of the parameters, workmem, for example, maxwell size. These are all parameters that are important for Postgres. Here I'm introducing another one, max parallel workers per gather. This is a parallelism parameter, and it gives you the maximum number of workers started by a gather or a gather merge node. So this is one of the parallelism parameters that exist in Postgres. There are multiple parallelism parameters in Postgres. And random page cost, which is another parameter that governs the planner's cost of a non-sequentially fetched disk page. So this is a parameter that affects the planner, and it gives you some information related to the disk, right? So the disk, that information is fed to the planner to then define the the way the queries are executed by the planner, right? So the plan for the query execution. And so these are two examples of parameters that affect the planner, but the disk as well, and the parallelism. There are other parameters that affect the memory and so on. And so all these parameters really affect kind of the runtime of the Postgres system itself. The issue is that this parameter is highly dependent on the application. So, and I would like to show this example here, where I talk about these two parameters that I just introduced, max parallel workers per gather and random page cost. And I show how these two parameters, if I explore different values of these parameters, and I show on the y-axis, sorry, on the vertical axis, I show the query runtime in milliseconds, so lower the better. I'm showing here that the performance that you get across this combination of parameters can vary quite substantially. So if you look, for example, the best area in the plot is the dark blue area, which is the bottom right corner. And the worst area is the yellow area. So if you optimize the system and you get a small max parallel workers per gather for this application opinions, which is a product review type of application, and you have also a small random page cost, this is the best solution for this application here, and you get the best performance, which is about 1 millisecond. If you do it wrong and you get a large max parallel workers per gather, for example, and a large random page cost, you will get into the yellow area, which gives you about an order of magnitude worse performance, right? So you're in the yellow area. So an order of magnitude worse performance by just basically changing these parameters, it's very substantial. So you can see this order of magnitude performance on the table also in a second benchmark called TPCH. So here, for example, we are showing that the performance of the best configuration is 1500 milliseconds. And then if you go on the yellow area, you go into the 12,000 milliseconds, which is roughly, again, an order of magnitude difference in performance. But there is a second thing that you learn as well from these plots, and it's the fact that the best configuration of the system has changed from the bottom right on the opinions.com application to the the bottom left for the TPCH application, right? So that basically means that if you have a customer or a colleague or a friend that comes and say, okay, well, I have an application, can you optimize this one for me? And you give them a solution. That will be great for them. But then if you have another friend that comes to you and asks you for a different for a different application and the tuning of a different application, and you give them the same solution, then you will not serve that second friend very well, because you're basically giving them a pretty poorly performing solution, right? So this is the case of application-specific tuning, which is really explained in this example. So the first thing that we learned from these two plots is that there is this order of magnitude performance difference between doing it well and doing it poorly. The second thing that we learn is that this is really specific to the application. So if you come from from application to another application, you need to redo the tuning again to really make sure that the performance is optimal. And then there is a third point, which is very often when we think about database administrators, when they do tuning, they often do this in a sequential manner. So they start with one parameter, they tune that parameter, they move to the second one, and then very often there is this sequential scan of the parameters, and that very often leads to suboptimal results because you basically moving in a coordinate parallel coordinate type of way through this plot, and this is basically not going in a diagonal way, and that means that if you scan the parameters in a sequential manner, you may miss the most important opportunity. That is, for example, on the opinions benchmark, for example, is on the bottom right, and you often, if you start from max parallel workers per gather equal 2 and you go up like this, and then you may miss entirely the interesting spot. So this is an interesting kind of couple of examples to show these three concepts, and I will move now into talking about the complexity that is increasing over the years. So the number of Postgres parameters in over the years has increased linearly. We have about maybe 370 parameters with Postgres 18, the latest release. Not all those parameters, though, are important for performance tuning. And I will argue that perhaps between 20 and 25 parameters are really important for performance tuning. And the point I would like to make, though, is that even if you look at just 12 parameters, which is a pretty small number compared to the overall parameter numbers, that the number of parameters that you should take care of when tuning, you really get to kind of a trillion possible configurations of the server. And that's a very high number. It's very tedious to explore that number if you're doing this manually, of course. And that's why the complexity is really important. And every time we have one more parameter, this complexity increases exponentially, as you can see in the shape of the curve. All right, so how is parameter tuning tackled today? So this is usually a manual process. It may take a pretty long time, days including, or maybe several hours or days, or even sometimes weeks of manual tuning, depending on the complexity of the application and the expertise of the team. And it's ineffective in the sense that you may need to tune again if things change in your application, for example, or if you're migrating into a bigger instance and things like that. So there are a number of scenarios where you need to tune quite regularly, and there are seasonal workloads as well. So the Thanksgiving workload is probably going to be very different than your usual workload, for example. And this is usually done by people like our colleague Magnus Sagander, for example. I call him the tuning guru, who is a person who has very much experience on doing this for perhaps a couple of decades. And in general, people that do this manually, they have a lot of experience. They have at least 3 to 5 years of experience in Postgres and Postgres tuning, and they go through that process. The second approach is a heuristics-based approach where you use tools like PGTune and Postgres Configurator. These are tools that are readily available online. PGTune is open source. You can basically use this, and it's based on rules. So if you have this much memory, or if you have this disk type of disk, and you basically push a button and it gives you this Postgres configuration file that you can then use directly in your Postgres instance. Of course, it's up to you then to take also responsibility if this configuration file will affect your system or not, and it's also up to you to define if this configuration file is correct or not. Correct meaning if it does the right thing for you, more than correct is it's effective for you, right? The problem is that this really uses generic rules and it's not customized to your specific use case. And so the third approach, which is a new approach that we are pushing at DBtune, is an AI agentic approach. And this is a solution that learns by observation, adapts to changing workloads, and automatically tunes your instance with minimal supervision. Okay, so there are a number of ingredients here that are very different from the the manual and heuristics approach. But this has really the potential of customizing the use of Postgres with respect to your own use case. And so this is kind of the general kind of desiderata of agentic AI for automated database tuning. So here you have a Postgres-specific AI and machine learning approach that learns how to solve Postgres optimization challenges. This is dynamic in the sense that it's workload specific. So if you come with an application or a workload, this gives you a solution. If you come with another application, it will give you a different solution that is optimal for that other application, right? And if it's easy to use in the sense that you don't need to have any background in AI or database tuning to make this work. And it's highly scalable in the sense that when you do manual tuning, you need to tune one instance at a time. But if you are using an agentic AI approach, you can basically deploy 1,000 agents for 1,000 instances. And these things are basically tuned all at the same time, which is really interesting, especially if you are a large enterprise company that has hundreds, if not thousands, of database instances. So the type of ROI that you can expect using an agent to tune Postgres are the following, right? So this is about achieving a faster application. I'm talking about the second one here, which is the most obvious one. You tune your instance, you get a better response time. And this can be sometimes all the way up to 10x better, right? And substantial performance, as I was explaining in the previous benchmarks. But there is also another aspect, which is if you optimize your Postgres database, this basically means that you don't need to over-provision to deliver the SLAs, over-provisioning the hardware, the infrastructure, to deliver on the SLAs that you have by agreement with your customers, right? And so that means that you can then right-size your instance, and this very often means that you can literally halve your instance. And we've seen some of these use cases where you can basically optimize your instance, and then you can shrink the instance. In the cloud, it's of course pretty easy to do so, and it's really great. The third point is that you increase the productivity of your team, because the team can save the time that they spend for tuning to do other things. And database administrators and database engineers are very busy doing many other things. So automating this one task that's very tedious and manual task, it's usually considered pretty good, and having a tool in your toolkit that you can use the same way you use other monitoring and backup solutions and so on. And if you optimize your software, this becomes also much more sustainable. Won't talk very much about this in this presentation, but there's a blog post that you can find the references here in this slide that it was written by Data Center Dynamics and talks about the impact of tuning databases on the climate. So pretty cool. How does this look like? So this is the agentic AI architecture for self-managed Postgres. So here, this is a self-managed Postgres, so you're managing it yourself. And on the left side, you have the Postgres instance. Then there is a DBtune agent here that is open source, and it contains two parts. It contains the monitor, which gathers performance data with respect to CPU usage, memory usage, and disk, and as well the pgstat statements metrics that come from like response time for specific query groups. And this is data that is not considered privacy sensitive. It's performance data only, and it goes through the optimizer learning activity, right? So the optimizer will learn from this data and get better at predicting what is the configuration of the server on the left side that needs to be used. And so the optimizer offers a recommendation. The actuator uses the recommendation to change the configuration of the server on the left side. And then the server runs for a little while. The monitor monitors the metrics, and the metrics get then reported back to the machine learning optimizer. So here I'm using specifically the DBtune example because this is really what I'm really familiar with, and we build this in the real world. And this is the agentic approach to database tuning, where you have an agent that connects with a bigger model that basically guides the optimization. And so this loop goes on for a little while, and then eventually the agent by design will disconnect and will not change the system anymore. So this is a all very controlled optimization phase where the database administrator or the database engineer will basically trigger this optimization. This will last for a few hours, and it will basically return an entirely tuned configuration. So this is really, really great. This is how it works for self-managed Postgres. In practice, though, the really good news is that you can do this also for any sort of like Postgres flavor. So you can use this in self-hosted Postgres, as we just discussed, but you can also use this in RDS, in Aurora, for other distributions of Postgres like EPAS, EDB EPAS, and Ivan, and Google Cloud SQL, and Flexible Server for the Azure offering. So the way this works, just to give an example, is a slightly different mechanism. So you still have the agent that connects to Postgres through the API. So this database as a service systems, they offer a pretty granular API that allows you to connect to the database service, and you can basically do this operation of changing the server parameters and monitoring the performance. And so the overall scheme is the same. It's just that the agent needs to connect directly through the API, and it can do so. So just to give an example of what this looks like on a synthetic benchmark, you have on the x-axis here, you have time, and this is about 3 hours in total. And on the y-axis, you have performance in transactions per second. So here, higher, the better. And you can see that the default RDS configuration here, we're using TPCC benchmark on RDS, on Amazon RDS. And so if you see the average so the performance of the M5 to X large instance running TPCC is about 850 transactions per second. If you double the size of that, you get on the green bar, which is the green line, which is the M5 for X large, and you get 1900 transactions per second. That's great. This doubled the performance. This doesn't happen all the time. When you double the size of the machine, you don't always get double the performance. But in this case, this is happening here, and that's great. If you use DBtune or an agentic AI approach to this problem on the small instance, the M5 to X large, what you see is that DBtune will start from the red, but then will explore the optimization space, and it will eventually converge into a performance which equates the larger instance. So with the smaller instance, you're getting the performance of the larger instance, right? So this is pretty interesting. And you can see that the other performance is flat. I mean, there is a lot of variability, of course, because systems are noisy, but in average, it's flat. Because RDS is not changing the configuration of the server based on your workload, but DBtune has a completely different pattern because it's exploring what works well for your workload and then providing the best solution for that workload. Okay, so this is a different framework for database tuning, and it's very exciting that we can now solve this problem with an agentic AI approach. This way. And if you look at the impact of this, of course, you have halved your instance size. There is also an economics type of discussion to be had here, because if you can do that, then of course on the left side here you have the hardware. So this is everything is double. You see the number of cores, the RAM and IOPS, everything is double. Then the instance cost is $6,000 for the small instance, $12,000 for the larger instance. The cost of disk EBS, and if you add these two numbers, you get the total. And this is roughly $8,000 per year just for one instance. And this means that you're basically saving 50% of your RDS cost by tuning your instance. And of course, if you have tens and hundreds of these instances, can really quickly become in the order of magnitude of millions of dollars in savings. And we know that some companies, of course, use 10, 20,000 instances. Large businesses, they may have that type of magnitude, right? Good. Let's now move into slightly more realistic examples. So this is an insurance application use case study from customer anonymized data. Here we have 16 CPUs, 32 gigabytes in RAM. It's an on-prem system, and it's a primary instance with running Postgres 15. So this is an instance that was heavily tuned manually first by an expert DBA, and then tuned with DBtune. So this was the idea of comparing how much more performance DBtune can actually give in a production system with an already tuned instance, right? And so what you see here is a plot that shows for each bar. This is one of the configurations that DBtune has run. And you get about 30 iterations in total, 30 configurations in total. And this whole thing ran from 9:40 a.m. to 2:55 p.m., right? So this is just in a few hours. And what you see here is that these are the configurations that have been explored. So the blue is the baseline. It's 0.85 milliseconds. You can see that you have things like random page cost of 4 and shared buffers, workmem, and all these other parameters. And then you get a speed up, in the green, you get a new configuration, which is a speed up of 2.5x. And you see that some of the parameters have been changed. For example, the max parallel workers parameters have been increased. Both of them, both the max parallel workers and the max parallel workers per gather. So the random page cost was reduced, and other parameters as well. So this is pretty complex to understand exactly what happened between the two configurations. Of course, there are explanations, but you see that the process is really changing all these parameters and making them better over time. And the blue versus the green gives this massive improvement in performance, 2.5x improvement in performance on a production system. It's pretty substantial. And this is from a baseline, which is a strong baseline, which is a manually tuned baseline. The second example is an example by PaperShift. So this is a use case that is publicly available. The PaperShift CTO wrote a blog post about this because he was very excited about being able to offload and that's actually words that he uses in the blog post. He says, I'm very happy to offload this task to a robot, right, into an agent that does it for you. And this was an Amazon RDS migration project, and they moved from an instance to a different instance type with 32 CPUs, 128 gigabytes of RAM, and Postgres 17.6. And the baseline is the RDS defaults, and here we have then automated. So they have automated, and they've done this whole process independently from us. So I'm just collecting the results here and putting them in the slide. So here, what you see before the average query runtime is here, 100%, and the CPU utilization is 80%. And what you see on the afterwards, you get the 50% in terms of average query runtime, and you get the CPU load that is basically almost halved. And so that's, I think, really interesting because the agent was able to not just optimize the average query runtime, which is this form of response time and maybe a form of latency that can affect, of course, the user experience and so on. So this was halved. So there is a double performance improvement basically on this workload. But there is also the second aspect, which is the CPU usage, which is also really important for having headroom for any situation where the workload may change and you want to have the ability to cope with more load. And so this is really, really interesting and insightful. So you can find the blog post link here in the bottom. A third example, which I think is really my favorite example here, this is a tuning of Amazon RDS instance. Again, a very large instance, very complex, 48 CPU cores and 412 gigabytes of RAM. So this is almost a terabyte of RAM on Postgres 14.17. And the baseline is the RDS baseline, and the green, which is in blue, and the green is the automated tuning with DBtune and the DBtune agent, so the agentic AI approach. And what you see here is that the performance gets improved from 75.9 milliseconds to 7 milliseconds, which is roughly a 10x. 10.8x, I think, if I do the math right, improvement in performance, which is very, very substantial performance improvement. And I think that the sheer performance difference can find someone to be surprising. The thing what is pretty interesting here is that, and it's becoming really, really apparent for us doing this kind of activity every day, is that when you get to more complexity here in this application is very complex with 48 cores and a lot of RAM and so on, a very, very demanding application. What you see is that the performance improvement that you can get with agents is actually higher usually. So you get higher performance improvement when you go on much more complex applications than just running, for example, a parameter tuning exercise on a PG bench example, right? So if you move away from simplistic benchmarks, you can get performance improvement that is much higher because the agent is able to uncover all these bottlenecks and all this kind of tedious, issues that the runtime system has and optimizes the way the disk is used, the memory is used, the CPU is used, but also the way the planner, runs the queries basically. So this is all I think for the experimental part, and you can find more information in the blog post as well. One aspect that it's very, very important when deploying agents in the real world is the safety. And safety really needs to be built before the optimization. And so we built a lot of mechanisms around the optimizer to make this process really, really safe. So parameters have very specific safe upper and lower limits. So this is not like writing a wrapper to ChatGPT that can tell you to go explore a random pitch cost of 25 without really having a good explanation for why. So this is all very constrained in a way that the artificial intelligence piece cannot just go wild and do whatever it wants. And the second aspect is the memory monitoring guardrails. And this is basically the idea that some of the memory parameters may affect the memory usage. And this is, of course, constrained by the first point, but also monitored in real time. And if the memory usage goes above a certain value, let's say, for example, 90%, then at that point, the guardrails will take the lead and bring this back to a safe operating mode. And finally, the optimization space can lead to slightly worse performance during the tuning session, right? And so you need to also have some sort of early exit condition for each one iteration to basically move on when you quickly see that the performance is not going in the right direction. So the performance degradation guardrails are important to avoid any degradation when the agent is running in a production system while the system is being used in the real world by real users, right? And so this can be basically done with no downtimes, with no risk of affecting the system through these mechanisms. And it can be done in a production system while it's being used by real users. So the tuning is not noticed by the users, basically, because it's all happening behind the scenes without affecting the performance of the system. So really, really interesting approach. So this is all I have for today. I would just like to reiterate on this idea that agentic AI is ready for prime time. It can be used in the real world, in production systems, to help anyone working with databases, database administrators, platform engineers, database engineers, developers, to tune your database. And there is a free edition that is available online that you can try. If you want to try these things out, please go to app.dbtune.com and try it out. Feel free to connect with me and ask questions on LinkedIn or via email if you wish. The future of databases tuning is AI assisted. So let's go and stop the manual tuning nonsense. Thank you so much.